Hi, this is CaJaDE, and I'm presenting Putting Things into Context, Rich Explanations for Query Answers using Join Graphs. This is a collaboration work with Zhengjie Qitian under the guidance of Professor Boris Glavich and Professor Sudeepa Roy. Explanations for query answers has become an interesting topic that continues to draw attention in the database community. Problems such as using relational database information to explain surprising query results like outliers has been explored in a variety of research works. Imagine you are an NBA data analyst and you are interested in the number of wins over the years for Golden State Warriors, and you would write such query that counts the number of wins and group by the season. Here is the query result, and as you might notice that there's a huge difference between 2015 to 16 and 2012 to 13 in terms of number of wins. And you might be curious about what could be the reason behind it. There have been methods proposed to answer surprising query result before. Most of the work has been focusing on using provenance. To put it simple, provenance is a collection of input tuples that contribute to the results of a query. Like here, provenance of two tuples of our interest are highlighted here. The provenance-based method then would try to find the selection pattern, which is a set of predicates with constants that compactively describe the pattern from a table. In this toy example, one of the explanations for one GSW wins 73 games is home points bigger than 100, which gave the hint that home team would have more points in 2015 to 16 season. This is merely a fact and does not provide any meaningful explanation to our question. In one of our previous work, we looked into an approach that goes beyond provenance, which tries to find the counterbalance point to explain the question. Like here, we find a linear relationship between number of wins and season. Then we choose data points that are in the opposite direction of the user question as explanations. It is useful in capturing the trend of the result, but still not useful in explaining the reason behind the success or failure of a team. These methods are useful, but they ignore important contextual information. In our NBA database, there are actually a lot more information that are not considered when generating the explanations. Like here, the provenance of the query only comes from game table. However, there are many relations that has connection with the game, but are ignored when finding the explanations. As an example, we can join provenance with player game stats table and player table. As you can see, we are adding players' information and their performance stats to the provenance. As you can notice, player Stephen Curry's points have greatly increased from 2012 to 13 season to 2015 to 16 season. In the real world, Stephen Curry was only a young player who hadn't realized his full potential in 2012 season, whereas in 2015, he had become the most valuable player in the league. A major player's development could contribute greatly in a team's success. Thus, this type of explanations can provide content that are not easy to think of, yet very informative and deep. Thus, we need more explanations like this. Introducing CaJaDE, the first explanation framework that leverages additional context from the relational database to explain query results. As an overview, CaJaDE first takes two query results as an input. Like in your example, the input is the number of wins from 2 seasons. Next, CaJaDE uses the provenance as a starting point and constructs joins to build an augmented provenance table. We call APT in short, as the input to our pattern mining step. CaJaDE then tries to find patterns that are good at both summarizing the information and differentiating the two query results. Like in this example, we have player Stephen Curry and points bigger or equal to 23 points, which perfectly summarizes the 2015-16 season because all of the tuples match the pattern description. At the same time, for 2012-13 season, none of the 5 tuples match the description. Thus, this pattern perfectly differentiates the 2 inputs. So how to bring things into context? To do so, we first introduce 2 definitions that serve as the building blocks of the context. The first one is a schema graph, which encodes the join conditions of the database. Such graph can be as simple as standard foreign key constraints. We also allow user to input customized join conditions. The second definition is a join graph, which is a multi-graph constructed based on schema graph to bring in the new context. Join graph all start with the query provenance node and try to join external relations. The join condition in the join graph should align with the join conditions from the schema graph. Join graphs then will be used as the blueprint to produce the augmented provenance tables, which will be used in the pattern mining step. As shown here, on the left-hand side is the schema graph of the NBA database. For all the relations accessed in the user query, we use provenance table to represent all of the relations, which we will call PT in short. Here in our example, the query only accessed the game table, thus PT represents game node. We then find viable join edges that exist in the schema graph to construct the join graph. As you can see, there exists an edge between player game stats and game, and also another edge between player game stats and player. Based on those edges, we can just build our previous example join graph. Given the ways to bring in context, we wanted to find patterns to summarize APT relevant for explaining the question in the join result. Then naturally we face the question, what makes a good pattern? Let's go back to our example. We identify 2 main qualities that a good pattern should have. The first is ability to summarize one of the input tuple. The second is good at differentiating between the 2 input tuples. To do so, we first select one of the 2 input tuple as the tuple of interest, which we call primary tuple. In this case, we select 2015-16 as our primary tuple. Then, given the pattern candidate, we use recall to indicate the summarization ability of the pattern candidate and precision to indicate the level of differentiation between the primary tuple and the other tuple. Now, given the player equals S and points bigger or equal to 23, the coverage of the pattern in the APT are highlighted in their respective colors. It is easy to compute the coverage of a pattern in the provenance without joins. In the APT where joins are involved, we face a unique problem. In certain APTs, tuples might have different number of join partners, which we call a scaling factor. The higher the scaling factor, the more join partners a tuple has. Imagine one tuple from the original provenance has only one join partner from the additional relation, whereas another tuple has 100 join partners with additional relation. If we treat each tuple in APT as only a fraction of the provenance tuple in computing the coverage, the ones with high scaling factor values would have a smaller coverage. In practice, it is hard to argue why the ones with more join partners should have less significance compared with the ones with a less number of join partners, and vice versa. Plus, the coverage very unstable across different join graphs because of the different join conditions. Based on those observations, we use the following covering strategy. No matter how many join partners a provenance tuple with additional relation has, We counted the coverage as 1 if among the join partners at least one result tuple matched the pattern, and 0 if none of the join partners would match. Given the coverage, we used F-score as a quality metric. In this example, out of 3 games in 2015-16 season, all of the 3 tuples have 1 tuple fulfill the pattern description. Thus, we have recall 3 over 3. In terms of precision, we notice that there are a total of 4 tuples in the join result fulfill the pattern description, and 1 comes from non-primary tuple, 3 from primary tuple. Thus, we have precision of 3 over 4. Given the previous foundations, we mainly face the following technical challenge in implementing CaJaDE. We have large search space, which comes from 2 aspects. First is number of possible join graphs. Second is number of candidate patterns. In evaluation step, we also run into a huge runtime cost in evaluating the candidate patterns over the APT. In a possible number of join graphs, we observe that exhaustively enumerate all possible join graphs is exponential in all degree of nodes. To give you a detailed idea, we assume that we have n nodes from schema graph. We also assume the nodes from schema graph have an average out degree of m. To further simplify, we assume PT only contains 1 relation. In the first step, since we only have 1 node, so we only have 1 possible join graph, contains only PT node. For the second step, since PT only contains 1 relation and 1 relation have an out degree of n, so we have n possible different join graphs in size 2. In the next step, since from previous step we have 2 slots available to extend an edge, so we have number of size 2 times 2n, and so on. We have recursively derived the relation from the previous step. So in summary, it is exponential in n. So how do we reduce the number of join graph candidates to process? We made the following solutions. The first is based on observation that complex joins, which means it has many edges, are hard to integrate. Thus, we limit the number of edges per join graph. The second observation is that we can safely skip some candidate join graphs that lead to redundancy. One possible redundancy is adding 2 identical edges to different parts of the join graph. And finally, we skip cross product caused by loose join conditions. The second technical challenge of the search space, we focus on the candidate patterns. We observed that given the size of the APT and number of attributes, the number of possible candidate patterns are exponential in the number of attributes. To exhaustively enumerating all possible patterns is infeasible in practice. Thus, we propose the following pruning strategies. Firstly, since we are bringing a context, it is necessary to include predicates that come from the context. So, in practice, we only consider patterns that has at least 1 predicate with constant from additional relations. Secondly, we start by processing patterns with categorical attributes first. The reason is that possible number of patterns that contains only categorical attributes is significantly smaller than those with numerical attributes. We can also filter out such patterns with low recall first, because we can only have worse quality scores by adding new predicates, and only refining those with high recalls by adding numerical predicates. Also, we only need to consider one of the many correlated attributes. For example, birth date and age are highly correlated. If we enumerate patterns for both attributes, the cost is tripled, but the patterns are telling the same story, thus lead to redundancy. Finally, we use random forest to select important attributes that help differentiate the two user input tuples. Our next technical challenge results from evaluating patterns. Specifically, the problem is that evaluate all candidate patterns over the full APT is expensive, because we have to repeatedly scan the full APT. Our proposed solution was to evaluate F-score over only a sample of the full APT. In the evaluation step, we did both qualitative and quantitative evaluations. In case study, we come up with 5 different queries for 2 different datasets to examine the applicability of our system. To give you a flavor, we asked why player LeBron James' average points dropped from the previous season to the next season. The system successfully captured the transfer of a player to a different team. For a mimic dataset, we asked why patients with Medicare insurance had significantly higher death rate than those patients with private insurance. The explanation was that give you our hint that for private insurance, the patients tend to be younger than those with Medicare insurance, which makes perfectly sense and align with the fact. In user study, we asked user the same question presented in the previous slide for Golden State Warriors winning records. The goal is to evaluate if we are providing meaningful explanations by bringing the context, and also to see if our quality metric is consistent with users' preferences. The setup is participants will rate 2 groups of explanations. The first group will be explanations based on provenance only, and second will be explanations based on augmented provenance. The main findings are user-preferred explanations from augmented provenance, and also quality measures are consistent with participants' preferences. And finally, our augmented provenance provides additional useful information. Based on the previous optimizations, we achieved a sublinear performance in terms of runtime in bigger scales for 2 different datasets. Next, we evaluated the efficiency of sampling on both runtime of the process and the accuracy of the top global patterns. As you can see, in both datasets, lower sampling rate can effectively decrease the total runtime. In terms of accuracy, we use NDCG score as the evaluation metric and global patterns generated without sampling as the ground truth, to see how relative ranking change by using sampling. The result shows that NDCG scores are still pretty high even with aggressive sampling rates. In conclusion, we've proposed the first step towards automatically exploiting contextual information for explanations. We proposed a set of optimizations to deal with large search space. We also examined the applicability, both conducting case study and user study. In future work, we want to bring in causality into consideration when generating the patterns. Also, we want to further refine the search strategy, such as bringing user in the loop or quality-guided search. And furthermore, we want to integrate context into other explanation frameworks. Thank you.